Here's a nice solid mechanics question, and this is something that first year engineering students might encounter. That's either students who are doing aerospace or mechanical engineering or ship science or something like civil engineering as well. And if you'd like to see anything similar to this on the channel, or if you have any suggestions for any topics or specific problems that you'd like to see, let me know in the comments. So this is a problem where we don't actually have numbers, okay? And we have a beam which is simply supported at point C and is sitting on a roller support at A, okay? And we have two external identical forces that are acting here and here, and we're trying to find this distance A, essentially, right? So we're trying to find the distance A such that the moment at B is equal to 0, okay? And as with any similar solid mechanics problem, the first thing that I recommend doing is to find the reaction forces. So I'm going to draw the free body diagram, and here's what we have. We've got a force P acting here. We have then a reaction force at A, right? So this is our A, and at A there's only a vertical reaction because there's only a roller support, as opposed to C, where you have a vertical reaction RCY and a horizontal reaction RCX, like this. Okay. And the other thing that we have is the second external force P. Okay. And then we have that this is L over 3, and this is A, and the entire length of the beam is L. Right, so let's try to first find the reaction forces. Now, the first thing that should be obvious is that RCX is equal to 0 because it's the only horizontal force, okay? And the other thing is that the sum of forces in the y direction is equal to 0, where up is positive and down is negative. So we have two forces going up, which is RA plus RCY, and downwards we have the two identical forces. So we have minus 2p equals 0, which should give us that RA plus RCY equals 2p. Okay, so that's one thing. And the other thing I'll do is I will apply moment equilibrium, okay? And I will take moments about this point here. You can take moments about any point, but as you will see, taking moments about point C will not only cancel the moment due to this force, but it will simplify the problem overall. So this is what we have. Sum of moments about C equals 0. So how many moments we have? We've got a moment due to this force, which is going to be counterclockwise, right? So we have P multiplied by the moment arm, which is L. And then we have the moment due to this force, which is going to be clockwise. So that's going to be minus RA times the moment arm, which is L minus A, like this. And then we also have the moment due to this other P force. So that will be plus P multiplied by the moment arm. Okay, and the moment arm of that is just L over 3. Okay, the distance between B and C. So that's L over 3, and that's everything we have. So this equals 0. So now let's try to rearrange this. So we have RA times L minus A equals, so I'm putting this on the other side, and now PL plus PL over 3 will be 4 over 3PL. Okay, so RA is therefore equal to 4/3 P times L over L minus A. I like writing it like this because we have, dimensionally speaking, we have that RA, which is a force, is equal to another force, multiplied by this and this, but this L over L minus A is a dimensionless variable, right? So it's a length over another length. Right, so now we're going to use this reaction to find what the question is asking us to do. Now, normally you would find this reaction force as well, but as you'll see for this particular problem, we don't actually need to do that, but you can if you want. So we're trying to find the moment at B, and because we have a discontinuity at B, right? In other words, we have a point load acting at D. I will consider a cross section somewhere here, okay? And the length from the left-hand side of the beam all the way to here is going to be called X, okay? And X, in this case, will be somewhere above point A, or to the right of point A and to the left of point B. Okay, so let's draw the free body diagram of that first of all. So we have this section of the beam, which looks like this. And then we have a point load acting here. And then we have the reaction force at A, which is like this. So this is the RA that we found previously, and we know what that is in terms of P. And then we know some distances. So this distance here is A, okay? Which means this distance from here to here is X minus A, because the total distance is X. And then what we have is that at the cross section, we've got two forces. Well, we have a shear force, and we have a normal force as well, but we know that's zero because there are no other normal forces acting. And we also have a bending moment, and that's the one we're actually interested in. Okay, now let's call this point here P. So we take a cross section at a random point. Actually, let's not call it P because that's the name of the force. Let's call it R. Okay, so let's call this R like this. So we're going to take moments about R, and we're going to find what the expression for this bending moment is. And because we're taking moments about point R, like this, we don't even have to find what the shear force is, because the moment due to this shear force cancels out because it goes through point R, okay? So we have the following. First of all, we have the moment due to P, which is counterclockwise. So that is P multiplied by X on one hand. And then we have minus the moment due to RA, because that's clockwise. So that is RA times the moment arm X minus A. And then we have plus this here, which is M, and that equals to 0. So now we have to rearrange to find an expression for M. Okay, so we have M equals, and then we're going to keep M on the left hand side, and we're going to move everything else to the right. So this is RA times X minus A, and then minus PX. So the moment is therefore RA, which is this. So that's 4/3 times P times, I think, L over L minus A. That's what we have. So that's RA, but then we multiply by X minus A. And then we have minus P times X. Okay. So I think I'm going to factorize P because it appears in both terms. And then I'm going to multiply the numerator and denominator of this by 3L minus A. Okay, so 3L minus A, and we end up with the following expression. We have 4L times X minus A minus, and then we have 3PX times L minus A. And this is divided by 3 times L minus A. Right, so let's see how much we can simplify this further. So we have that M is equal to P times, and then we can expand this a bit. So we have 4LX minus 4LA, and then minus 3, I think there's a P here, that's it shouldn't be there. So that's minus 3xl plus 3xa, okay? And that's divided by 3 times L minus A, right? So let's see what else we can do here. We have 4Lx and minus 3Lx, so we get just Lx, and the rest of it is 3xa, and then minus 4La, and then we have plus Lx. And the whole thing is divided by, well, we have the p in front, and the whole thing is divided by 3 times L minus A. Right, so that's the expression for the bending moment as long as my x is somewhere between A and B, okay? So what we do now is we have to put the condition that the moment is 0 when x is this much. So when x is this long, right, we must have a moment of 0. So we have to find the length of this blue arrow, which is quite easy to do because we know this is L over 3, which means that this is 2L over 3. Okay, so when x is 2L over 3, the bending moment is 0. So now we just substitute that in here. Right, so we have 0 equals 2, and then we have p multiplied by, and then 3, and instead of x I have 12 over 3 times a, and then I have minus 4La, and then I have plus L times 12 over 3. And the whole thing is divided by 3L minus A. Now we have a fraction being equal to 0, so the only way in which a fraction can be 0 is if the numerator is 0. So let's just separate the numerator. So we have, can cancel out a few things actually. So we have 2La, right, because this 3 and this 3 cancel out. So 2La minus 4La, and then we have plus this last term, which is 2/3 L squared. So 2/3 L squared, and this has to equal 0. Now, obviously, L cannot be 0, so we can just cancel it out. And we end up with minus 2a plus 2/3 L equals 0. So we can move things around, and we get 2a is 2/3 L, which means that finally a is L over 3, or how the question wanted us to write this is as a fraction of L. So a over L is a third. And that's the final answer. So in other words, if this roller support is 1/3 of the beam away from the left-hand side, right? In other words, if this distance is the same as this distance, then it turns out that the bending moment at point B is actually equal to 0. And that's the end of the question.